Now that we know about isotopes, that is, elements with the same number of protons but a different number of neutrons in the nucleus, it's interesting to look back at our table of relative atomic masses. For instance, here's two entries, carbon-12 and naturally occurring carbon. They have different relative masses. That's because I could take a sample of pure carbon-12 where every atom is carbon-12, and that would have mass 12. But in naturally occurring carbon, 1 out of every 100 atoms is a carbon-13. It's slightly more massive. So if I took this piece of carbon and I started picking out atoms, 1 in 100 would be that carbon-13 with a slightly more massive nucleus. That's what gives this naturally occurring carbon that slightly higher relative mass. It's the mass-weighted average of all the isotopes. And you can see many elements have a potpourri of different isotopes. They don't have integer molecular masses and atomic masses because of the presence of all the different isotopes. Now, for the most part, isotopes are chemically similar. That is, they do the same chemical reactions, but of course they have different masses. A lot of times the mass difference is very small. For hydrogen, there's hydrogen with mass 1 and deuterium with mass 2. That's a factor of 2 in mass. That's very large. But for carbon already, carbon-12 versus carbon-13, that's a 1% difference in mass. That's relatively small. If you go to a very heavy nucleus, say uranium for instance, two naturally occurring isotopes are uranium-235 and uranium-238. That's a very small percentage difference in mass. Now, you can separate pure isotopes, and this is very common. For instance, uranium is a good example because we take uranium-238 and we separate out the other isotopes, and we make pure uranium-238. It's called depleted uranium because the radioactive fissile nuclei are removed. The uranium-238 is very dense, and it's used in armoring for the military because bullets and projectiles can't penetrate it. The uranium-235 is the fissile nucleus. It's used in nuclear reactors. So we have different properties of the nuclei that are different isotopes. Chemically, they're very similar, but sometimes their mass gives them different physical properties that we can use. In general, we catalog them based on the potpourri, the mass-weighted average of all the isotopes in the mixture. And that's how we achieve relative atomic and molecular masses.